Hi everyone! In today's video, we are going to talk about uniform accelerated motion, short as UAM. But before delving into UAM, we should know two basic formulas. The first one is speed equal to distance over time, and the second one would be velocity equal to the displaced over time. For the first formula, we are calculating using scalars. And for our second formula, we're calculating using vectors. If you still haven't grasped the difference between scalar and vector, please do refer to one of my earlier videos to check out. Now, we need to identify one very important thing, is that these two are used in uniform motion scenarios, which means that the speed or velocity, if we are talking about vector, remains constant. So we are traveling in constant speed all the time. But what if the velocity of a motion is constantly changing in a steady rate? Such as if a car is accelerating or braking, or we are skiing down a hill, our speed is always gradually speeding up or speeding down in a fixed, steady rate. So now we need to introduce another very important concept in physics regarding kinematics, which is today's video's topic, acceleration. And we define acceleration as the rate of change in velocity. So now, how do we calculate acceleration? So since acceleration is the rate of change in velocity, we need to think about our general thought process when it comes to rate of change. So whenever we think about rate of change, we always are trying to use the total change in the entity that we're trying to find the rate of change of over the total time it takes to change this entity. Such as if we have, let's say, 2 apples, and after 5 seconds, it becomes 7 apples. So, in what rate did we add more apple into this system? So we can see that over the course of 5 seconds, there are 5 apples in total that's being added into the system. And it takes 5 seconds to actually add these 5 apples. So we actually know that for each second, 1 apple is being added to the system. So the rate of change of the addition of apples into the system is 1 apple per second. Same logic applies here. So we can actually say that since the acceleration is just another fancy term for the rate of change in velocity, we can actually say that acceleration, which is a vector, just a heads up, is equal to the total change in velocity over a certain course of time over the total amount of time it takes for this velocity to change, either increase or decrease. And then we can actually make it more explicit. If we want to calculate the total change in velocity, we actually want to use the final velocity minus the initial velocity over delta t, which is the change in time. So this would be the formula for acceleration. Let's take a look at a few example questions to see how we can apply this formula and manipulate these variables in different scenarios. Example question 1. An object traveling at 150 km per hour east slows to 10 km per hour east in 5 seconds. What is the acceleration in kilometer per hour per second and meter per second squared? So before we delve into this question, we actually also need to familiarize with the unit used for acceleration. So we can actually apply for a unit dimensional analysis for the understanding of the unit. So we can actually see that since the acceleration is equal to delta v over delta t, that is actually meter per second used for velocity and second used for time, which would give us a meter per second over second as the unit for acceleration. And we can actually see that this is actually meter per second squared. So this would be a commonly accepted unit for acceleration. So now let's delve right into this question. So how can we do this? So first we can see that neither of this data right here nor this data right here is in SI units. So we really want to convert them into meter per second first. So how can we do that? So first we can see, still using dimensional analysis. So 150 kilometer per hour, we want to get rid of this kilometer and get a meter here. So we can actually see 1 kilometer equal to 1,000 meter, right? And we want to get rid of this h, and we want to use second instead. So we can see that 1 hour is actually equal to 3,600 seconds. So if we do this calculation, we can see that kilometer cancel out, hour cancel out, and we have meter per second at the end. So ideally, this would give us an answer of 41.6 repeating meter per second. And the same conversion would be applied for 10 kilometer per second. And we would get an answer of approximately 2.8. So let's say 2.7 repeating actual meter per second. And we can see that since this object starts from 150 kilometer per second and goes to 10 kilometer per second, so this is actually the initial velocity, and this would be the final velocity. So now we want to actually list everything we know, and this is actually a pretty good habit in physics, especially when it comes to harder and more challenging questions later, when we actually know many different equations applying for the same topic, and when we are choosing what equations we want to use, listing all the variables and known data out could be really helpful. So we can actually do some practice here. We have initial velocity of 41.6 repeating meter per second, final velocity equal to 2.7 repeating meter per second, and we have time equal to delta t equal to 5.0 second, which is right here, and we are looking for acceleration. So now we can apply our formula. Acceleration equal to delta v over delta t equal to v final equal to v initial equal to delta t, and now we just simply substitute the value in. We have 2.7 meter per second minus 41.6 repeating meter per second over the course of 5 seconds. And if we do the calculation correctly, we would get an answer of approximately negative 7.78. Let's round it to the 2 significant digit, so it will be negative 7.8 meter per second squared. And now we want to understand what's the meaning of the negative sign. So if we have a negative sign in the acceleration, this is actually means that the direction of this, since the acceleration is a vector, so it definitely has a direction. And the negative sign actually indicates that the direction of this acceleration is against the motion of this object. So we can clearly see that this object is certainly speeding down. So if this object, we have an object here, and this object is actually going this way, it's actually slowing down. And what's so interesting is actually the acceleration acts on the opposite direction, which acts against the actual motion of this object. And the reason behind this would be talked later on in dynamics. It's related to force. But now you just need to know if it's a negative sign, it means that the direction of this acceleration is actually against the motion of this object. Next example. An object accelerates from rest at positive 4 meters per second squared for 10 minutes. What is the object's final velocity? So again, we want to list our variables, or not variables, our known data out. So we have this 4 right here. This wording is a type right here. It should be 2. So we have this rest, which is a very important hidden information. 4 meters per second squared, 10 minutes. So the initial velocity should be 0 because it's from rest. Final velocity is 4.0 meters per second squared. And the total time, sorry, my bad. There's no wording question in this question. No wording problem. So the rest is still initial velocity, no problem. This 4 is actually, instead of final velocity, is actually the acceleration of this object. And over the course of 1 minute. And this minute is not in SI unit, so we want to convert it to 60 seconds. And we are looking for the final velocity. So, as we have our formula written down like this, we actually want to start rearranging our formula to isolate final velocity. So how we do that? So first, we can multiply delta t to both sides. So we can get rid of this denominator right here. So we will get something like a times delta t equal to final velocity minus initial velocity. And then we want to plus initial velocity to both sides, so such that we can get rid of this initial velocity on the right side. So we will have acceleration times delta t plus the initial velocity equal to final velocity. And now we can actually start substituting our values. So since final velocity equal to acceleration times time plus the initial velocity, so we can actually start substituting evaluating. And after a simple calculation, we will have the final velocity at a 240 meter per second. Example question 3. A rock is thrown upward with an initial speed of 12 meters per second. How long will it take for the object to get to its maximum height? So, this question is actually related to something very similar to freefall, which is another topic we will talk about in my next video about projectile motion. So we will not worry about this in this topic, in this question particularly. We will just try to apply the general acceleration formula. So still starting by listing our known data. Initial velocity, 12 meters per second up. And then we have maximum height. It seems like, and we are looking for t, delta t. It seems like this is the only explicit number that we can obtain from the question. What about the implicit number? So the tricky part in this question is that this ball, or sorry, this rock is actually thrown upwards and then slowing down gradually and coming to a approximate stop, and then come back down and spinning up, something like this. So this rock goes up first and then goes down. So you want to recognize that if we want to find the maximum height, this is actually a temporary stop. So the final velocity at the top would be 0 meter per second. What about any other implications of this question? What would be the acceleration in this question? The acceleration in this question would just be the gravitational acceleration, which is a very useful constant in physics, 9.81 meter per second, and always pointing downwards. Okay? So now we have two directions in this question, up and down. So we better define, let's say, up is always positive. That's good enough. So if we are looking for delta t, we still want to start by isolating variables. So what we're trying to do is first multiply delta t to both sides to definitely get rid of the denominator first. And now we will actually want to divide both sides by acceleration, such that we will have delta t equal to v final minus v initial over acceleration, and we can substitute our value in, which is 0 minus 12 meter per second, and up is positive, so it's just minus 12 meter per second, over acceleration 9.81, which is pointing down, so as we previously defined, it would be negative. So after a simple calculation, we will have approximately 1.22 seconds for this one. And since time is a scalar, so we do not need a direction. So this would be our final answer. So these would be three classical questions tackling the application of the general formula for acceleration. But there are still other extremely useful equations for harder UAM situations, especially when it comes to free fall, which is vertical projectile motion, and horizontal projectile motion. So we actually have three ways to calculate displacement. So in these four formulas, S denotes displacement, U denotes initial velocity, V is actually final velocity, A is acceleration, and I think that's basically it. And this kind of systems of equations or usage of variables would be specifically used for International Baccalaureate physics program, IB physics program. They like to use these variables to denote VI, VF displacement. Instead of D, VI, and VF, they use S, U, and V. So we actually have three other formulas to calculate displacement. The first one, displacement is equal to initial velocity times time plus 1/2 acceleration times t squared. The second one, displacement equal to final velocity times time minus 1/2 acceleration times time squared. Third one, displacement is equal to 1 over 2 bracket initial velocity plus final velocity bracket times time. And the last one, final velocity squared is equal to initial velocity squared plus 2 times acceleration times displacement. And these formulas will be used in my next video about projectile motion a lot. And I think that's all for this video. Thank you very much for watching and have a good day.